We're here to talk about WebTransport and Web Codecs. There's a group of us who have been working on this really for a few years now, and I'd like to let each of them introduce themselves. We have Peter Thatcher of Google. Hi, Peter.
Hi. I've been working on WebRTC for a long time, and I really like pushing things forward with new APIs that explore new use cases and things people are trying to do that they haven't been able to do before.
And Seth Hampson of Google.
Hello. I'm Seth. So we're also working on WebRTC. Specifically, I guess I'm here because I worked on the RTC Quick Transport, which is the standalone transport, P2P transport built on top of QUIC in Chrome, and it's enabled in the origin trial right now.
And Robin Raymond, who was the creator of ORTC that we've chatted about on ClueCon Weekly before. Robin, do you want to introduce yourself?
Thanks, Bernard. So I've been working mostly with the ORTC community group and helping to work on the next generation APIs for WebRTC, where WebRTC is going, which is why I'm here.
Yeah, and I should say that this effort started out in the ORTC community group to add Quick Transport to ORTC, and we're going to show you some diagrams and also talk about a peer-to-peer trial that basically accomplishes that. I'm Bernard Bobo of Microsoft, was involved in the Edge implementation of ORTC, and also been working with Peter in the ORTC community group. Steve Anton and Victor Vasiliev are not here today. But Steve works on ICE implementation in Chrome, and Victor works on a lot of protocol things relating to HTTP3. Is that accurate, Peter?
Yeah, he's kind of our go-to guy for quick stuff.
Yeah, Steve's also helped a lot with the Quick Transport, and he's also working a little bit with the new web codec stuff that Peter's going to be talking about.
So what are we going to try to cover today? Well, we're going to tell you a little bit about QUIC, the kind of innovation that it offers. Basically, QUIC is the biggest move forward in internet transport since TCP was defined in 1981. So it's a very big change. It offers some pretty amazing capabilities, and so we'll be talking about that. We also will be talking about an origin trial for QUIC APIs in Chrome, and that also appear in Edge Preview, so you can use it in either browser. Those origin trials now support both reliable transport, reliable streams, as well as datagrams. The origin trial is based on the ORTC model, and there are some links here to demos of both reliable streams and datagrams, and Seth will be showing you a demo, his own demo, in a little bit. These are available through Chrome version 73 to 75. The origin trial is up at the end of July, so we encourage you to go register, and Seth will be talking about how to do that so you can write your own demos yourself. We'll also be talking about coming attractions, WebTransport, which is a client-server version of the peer-to-peer QUIC APIs, and Web Codecs, which, if you're familiar with ORTC, kind of splits the RTP sender and RTP receiver to give you new capabilities by giving you access to encoding and decoding. So, a little bit more about QUIC and why it's so exciting. So, what is QUIC? Well, the first thing you should know is it's the basis for HTTP3, which is basically HTTP2 over the Quick Transport. So why was it necessary to find a new transport for HTTP? Well, as you may know, when you load a web page, that web page can be comprised of dozens or even hundreds of components, each of which was creating its own TCP connection and going through slow start to bring down that component. And that slowed things down enormously. So it made more sense to have a single connection setup, which could be much faster than TCP plus TLS. And that's what QUIC gives you. So quick connection setup is 1 RTT if you haven't contacted that server before, and 0 RTT otherwise. It also enables many reliable streams to run over the same transport. And so the result of that is when you're loading all these components of a web page, it happens enormously faster. Now, QUIC in its 0 RTT or 1 RTT mode looks a lot like TCP Fast Open and TLS 1.3. However, it's much more easy to deploy because it doesn't have any reliance on operating system upgrades. Now, one of the things that's also been observed about GQuick, which is Google's implementation, is that it has much better loss recovery than TCP. And this makes networking possible on networks that otherwise would probably fail using TCP. And the result of that is if you're doing streaming media, you'll see a lot fewer stalls. The web won't pause or fail. And there's a number of reasons for it, but one of the things that particularly contributes is what's called tail loss probes, which can avoid triggering RTO, false RTOs. And also the ACking is much better. You can get up to 256 NAC ranges, which makes a big difference if you've got a lot of loss. Now, another thing is that QUIC is secure by default. And that means that you're always secure. There's no equivalent of HTTP, only HTTPS over QUIC. With a recent extension proposed by Apple, you can get unreliable and unordered datagrams as well as reliable streams. If you use it with ICE, which is what we've done in the Origin trial, you can get peer-to-peer operation. You can also do client-server, which is more like a replacement for WebSockets, and we'll be talking about that. We call that WebTransport. QUIC is already widely deployed, mostly within Google, but there are many other implementations in progress, and it's very likely that it will have huge uptake once the IETF standard completes, which hopefully should happen during this calendar year or the next one. So today we have two major data APIs used by real-time programmers. One is WebSockets, and another is RTC Datachannel. These two APIs have a lot in common. They use a very similar messaging API. They also have a great deal in common with respect to their drawbacks in terms of congestion control. Both of these, WebSockets runs on top of TCP and RTC Datachannel on top of SCTP. In practice, they use new Reno congestion control. And that is problematic because the goal of new Reno is to build sending rate until loss occurs, which means they build queues. And they also compete with audio video due to the algorithm. And they also, both of them, will cause high latency due to head of line blocking. That is, in WebSockets, you have to go create another TCP connection every time you create a WebSocket. And it's even on HTTP2, you really can't use streams effectively over TCP because of the head of line blocking problem. So in addition to those issues, RTC Datachannel has been difficult for developers to use in client-server scenarios. That is, you've got to get a stack that runs ICE and DTLS and SCTP, and it's very difficult to run in production. It's also a pain to set up on the client today because you have to do SDP negotiation even if all you want to do is set up a data channel and transfer some data. The overhead of SCTP plus DTLS plus UDP is pretty high. It's 60 bytes per packet, and that's a lot, particularly in situations where you only want to send a small amount of data, such as in a game. And also, both the RTC Datachannel and WebSocket APIs don't handle back pressure effectively. So that makes it very difficult when you're doing a large data transfer, and there are also bugs in SCTP implementation which make that difficult. So QUIC offers the possibility of both having superior data transfer in peer-to-peer scenarios, as well as offering WebSockets-like capability with better performance and lower latency. So with QUIC, you can get both reliable ordered support and unreliable unordered through the datagram extension. It's also much easier to deploy in a client-server architecture because, as we've said, we're going to have multiple implementations of QUIC both on the client and server that you could use to do that. You get the same security properties that you had with RTC Datachannel and WebSockets. That is, everything's encrypted. You get congestion control on cores, so there's no loss there. But it's a lot faster because of all of these improvements that have been made to the transport algorithms. Now, what we started out to do was to create a new API, and that enabled us to fix things like the back pressure problems in both RTC Datachannel and WebSockets. Then the two APIs that we came up with was something called WebRTC Quick, which is a peer-to-peer API. And then for the client-server API, we have something we call WebTransport. So as a result, you can do a lot of things with these new APIs. And we'll also be talking about other things that you can do with the addition of web codecs. Peter?
Yeah, so one way to think about this is to consider the difference between web and mobile and what you can do with mobile APIs and web APIs. With mobile APIs, you can more or less do whatever you'd like in your app. There are not very many restrictions. But on the web, you're constrained by, in the case of real-time communication, with the WebRTC API. And some examples of things that you can't do easily right now are things like end-to-end encrypted group calls, controlling of your buffering or latency, adding custom processing into your pipeline like custom error concealment, combining synchronized audio, video, and data, and in non-RTC use cases, doing things like live streaming or cloud gaming. They are possible, but they're difficult. So over time, we've tried to expand what WebRTC is capable of doing by providing the application developer with more control or more flexibility. And the progression has been toward lower and lower APIs. So we started off with WebRTC, which is a fairly high-level API, and then we started and standardized and partially implemented the ORTC API, which was lower level, avoided a lot of the more unpleasant parts of the API and also gave the developers more control and flexibility. And now with WebTransport, we're going even further in making that low level and breaking apart the transport and the media parts of the pipeline that's inside of WebRTC. So WebTransport is a generic term for this idea of having a new API that's lower level that has QUIC underneath, but can also have other protocols underneath, and can either be client server or peer-to-peer. And the other half of that is this thing that we call codecs. But for now, we're talking about WebTransport. I'll talk a little bit more about web codecs a little later. So I'd like to turn it over to Seth to explain a little more detail about the RTC Quick Transport, which is the peer-to-peer version of this API on the transport side.
Yeah, thanks, Peter. So basically, I'm just going to overview the RTC Quick Transport, which is the peer-to-peer version of the web transport that Peter's talking about, and it's built on top of ICE, which is the RTC ICE transport. So the cool thing here is these are both standalone objects, so they don't, unlike pure connection, and they don't use SDP for signaling. They just have parameters. So right now, this is enabled in origin trial in Chrome, like version 73 through 75. You may be asking what an origin trial is, and it's basically a way for Chrome to expose new experimental web APIs to specific origins in the web. So it's basically like a safe way of deploying new experimental features and allowing people to try these out. So anyone can go to your origin and use this new API. But I should also note that you can actually experiment with this yourself if you want by just turning on the flags in Chrome. It's experimental web platform features. And if you'd like to experiment with it now while the origin trial lasts, it lasts until the end of July. So if you would like to do that, go out and try it now, and we'd love to hear your feedback. Basically, you can see from this diagram, like the general overview. So there's like some secure signaling that basically signals ICE candidates and pre-shared key for QUIC. And then you get an ICE connection, and the QUIC connection is built on top of the ICE connection. And then you have like quick bidirectional quick streams on each side, and also datagrams if you just want to send messages. So we have some more information here. The announcement is the blog post I made for the Origin trial. I also have this GitHub, which has Origin trial documentation, as well as a demo page and some like sample examples. Peter has this server up that's almost works for speaking to the peer-to-peer version. And there's also the specifications. So right now, what I'm going to do is show you some of the documentation as well as take you through the demo itself. So let's check it out. So what I'd like to do is just show you through the documentation and demo I've created. Basically, this is just a place to point developers to who want to either experiment locally or get an Origin trial token and experiment with the API. So what it is has a README, and on the top here we have like some Origin trial documentation. I point to the specifications here, and I give some information like how to actually get an Origin trial token. You have to request one for your specific origin, and then you basically just like put it in your HTML in a meta tag. So if you want to do that, I can just do it really quick to show you how. So you go to request this link right here, and then RTC Quick Transport. You register here, and you sign up, and you get a token right away, and it should work fairly quickly so that your origin can actually use the new APIs.
That's super simple.
Yeah, it's pretty neat. And then if you want to experiment locally, you can actually just like go to Chrome flags and enable the experimental web platform features or run Chrome locally with this flag. I've also included some like an API glossary because the API does differ a little bit from the spec. So this is like the point of truth for if you want to use the API. I have like all the methods, attributes documented, as well as some basic examples for reading and writing. Also in Chrome 75, we have datagram support for the Quick Transport. So if you do want to like read and write with unreliable datagrams, which is really neat, have like just a little short documentation on how to do that there. Cool. So let's check out the demo. What we have here is a file transfer demo. Basically, it's like really simple. It just uses a quick stream to send a file. So we can just pull one up really quick, send like a big video. Then you can go down and look at stats. It's kind of neat. So it says like number of incoming streams created 1, outgoing 1 here. And actually a neat thing you can do is you can pause from sending on the receive side, and it actually incorporates some back pressure, and it'll stop sending on the send side. Basically what that is our JavaScript's API is built so that if JavaScript freezes, we don't want to unlimited size buffer, and we also don't want like no buffering. So what we did was we incorporated like an arbitrary buffer size, and if we do want to change this, we could change the API to expose this sort of thing, but right now it buffers up to like 6 megabytes. And once that buffer has been hit, it'll actually, the flow control will send to the send side to stop sending. So you can see like we start receiving, like reading out the buffer data again, and it continues to send. It's kind of neat. And the other neat thing is you can do like multiple videos, and since they're all sending across separate quick streams, there's no head of line blocking, so they all send, which is pretty cool. Like pause one, restart it. Yeah.
Wow, that's awesome.
Yeah, and then you have all your stats to look at as well. If you want to just play around and have some fun, definitely go for it. The main reason we have this demo, I think, is not just because it's cool, but just like a place to point developers to, so you can actually look into this code. And if you go to here, it says like writing, reading. So you can go to this function, and you can see like what it's doing is it basically first writes the file name and then the file size. So you go into the like how the file is actually written. As I said, like you wait for a write buffered amount, so your write buffer is not full. Once it's been written out, it'll empty that buffer, and this promise will get resolved, and then you can actually write data. And then also, like, we update the progress bar and like calculate how fast it's sending. And then if you go to the receive side, you get a similar style API where we wait for a chunk size and then read it and stop reading once we send the fin bit across. So definitely check it out. And yeah, like, have some fun with it, play around. There's also the other demos we pointed to in the slides, so you can check those out as well. Yeah, that's about it. And the main thing here is we'd love to get like feedback on the API. So if you like want to play around with the API and give us feedback, that would be great. Sign up for the Origin trial and just get involved.
Okay, so like I was saying before, we have this API in the browser called WebRTC, and it's kind of high level. There's also another API in the web browser called Media Source Extensions, which is often used for streaming video, and that's kind of high level. But we found that a lot of use cases where people want to stream video, they want to do so with very low latency. And so some people try and take MSE and push it to its limits of becoming lower and lower latency, and others try and take WebRTC and adapt it to video streaming rather than real-time communication. And neither one of them quite fits. And so exploring what APIs we could give them, people trying to do these things, led us to not only take this peer-to-peer quick transport and turn it into a client-server version, but also add this idea of web codecs, which are low-level media codecs that can work for both the cases of real-time communication and of video streaming, because it's more flexible being a lower-level API. So let me demonstrate that, showing how these things work in a live streaming context. It's a bit of a simplification compared to real-time communication because it's only one directional, but you can imagine video and audio flowing in both directions, which is basically what a real-time communication session or conference is. And like I said before, there's a gap between mobile apps and web apps. And for mobile apps, this is what you see. Basically, you see transport, which goes straight down to either UDP or TCP, in this case, on the slide, UDP. And you see media codecs at the bottom. And so we want to do the same thing for web, to give you web transport and web code. So today, if somebody's using WebRTC for live streaming or cloud gaming or something like that, typically there's a server sending the media down to the browser over the protocols of ICE, DTLS, and SRTP. And pretty much nowhere in the media path is there anywhere for the receiving client to control how things happen. So it's not very flexible, and that's one of the things that is difficult for people using this for live streaming, in addition to people using it for advanced RTC applications. So what some people have chosen to do that you can do with one-way live streaming, but not two-way, not RTC, is that they use the data channel of WebRTC, which uses ICE, DTLS, and SCTP, but then they use media source extensions for the decode and render. This gives them more flexibility because the decode or the media side is separate from the transport or the data channel side, and so they can control more of the media flow on the client side. However, media source extensions wasn't really designed to be used in such low latency mode, and in order to make it work, it involves kind of various implicit behaviors that are only specific to some browsers. They are working on that, making it explicit controls, but there are still problems with the WebRTC data channel where it's difficult to use in a client-server context. So that's kind of where WebTransport comes in. And some people have chosen even to use WebSockets because it's easier to use on a client-server, even though there are problems with head-of-line blocking and congestion control, as Bernard pointed out earlier, since it's based on TCP. Others have chosen to bypass both WebRTC and media source extensions for decode because and use WASM in order to do both encode and decode, actually, because it gives them the maximum flexibility. The problem here is that they run into performance problem where they don't get as much performance or battery life as you would by having the codecs built into the browser. So what we'd like to do is basically take this picture that has the maximum amount of flexibility, but return the performance characteristics of unreliable delivery via WebTransport with QUIC underneath instead of TCP, and web codecs being basically the same as having the codecs in WASM, except they're faster and more power efficient. So that's what you see here, where QUIC is going between the server and the browser, and in the browser is WebTransport and web codec. And beyond that, the JavaScript or the application has full control over how the media flows across the wire and how it's deserialized and buffered and so forth. So it gives kind of the maximum flexibility with all the good performance characteristics. And if you imagine this going in two directions, where there's not just decode on one side but encode on the other, then it falls out into a real-time communication framework that is also maximally flexible but maintains performance. So what we'd like from developers is to know what pain points would be solved by having these low-level APIs or by having QUIC. We prioritize what we work on based on developer feedback. So the more feedback we get, the higher priority that this work will get. It's the kind of work that we'd like to do because we feel that it's going to provide application developers with the flexibility they need long term. But the more feedback we get into specific use cases and specific people that would like to use it, the more we feel that it's necessary or urgent. Similarly, if there are things that developers want from a low-level API, it's good to let us know, especially now when we're considering what the API should look like, before we get too far in designing and implementing them without considering some uses that people might have that we weren't aware of. And finally, we'd like people to use the origin trial and give us feedback on it. The more people that use the origin trial, the more we see that there's demand for it, and the more we prioritize the work of these things.
Thank you guys so much for coming on and giving us that great presentation. Developers, be sure to check this out and give your feedback and test that Origin demo and give your feedback on that. And are any of you planning on stopping by ClueCon Weekly? Or no, ClueCon, not ClueCon Weekly, ClueCon in Chicago. You guys, you three.
I'm not sure yet. Love to go. I love Chicago, but I'm not sure yet. Depends if my schedule will allow it.
Okay.
Kind of the same.
Right on. Okay. And Bernard?
Yeah, unfortunately, I can't make ClueCon this year, but hopefully next year.
Okay. Well, we'll miss you. Thank you guys again for coming on. That was really great. So we'll catch you guys next time. Thanks again.
Okay.
Thank you.
Thank you.
Bye-bye.
Bye.
Thanks for watching ClueCon Weekly. Don't forget to give this video a like and a subscribe. And while you're at it, make sure to go and follow all of our other social media channels. We'll see you right here next week, same time, same place. And catch you at ClueCon.